Well, good morning, everybody. Today I'm going to talk about Websnark. Websnark is a very specific library, mainly to work with zero-knowledge proof in the browser. As many of you know, zero-knowledge proof are very important for many of the applications. It gives a lot of so it seems very important, for example, for scalability. I think during this conference we will have a lot of chances to talk about that. But they also make a very important role for privacy. For example, here are some of the applications that make a lot of sense to work with zero knowledge. Voting applications, identity applications, of course, mixers, private transactions, some games. But in the scalability, for example, we can think also for a light wallet where you can prove all the chain with a single zero knowledge. That would be great, for example, because the wallets will not have to download anymore the full blockchain or even the headers of the blockchain. They just take this zero knowledge and they can verify it in a constant time, milliseconds. Okay? So how, well, beforehand, I want to explain a little bit how a zero knowledge works. I'm going to do a very short introduction, but it should be clear. So mainly a zero knowledge, we start with what we call a circuit. Sometimes it's a statement. It's a deterministic program. We have inputs, outputs, and mainly what we want to do is prove that we know an input whose result is the output, but without revealing the input. In general, in a normal circuit, this makes no sense. If I do an addition, it's very easy. Well, it makes no sense to prove that you know two numbers that the addition is 4. Everybody knows that. It's reversible. But zero knowledge makes a lot of sense when the circuit, when the statement that we want to prove is not reversible. For example, the most simple circuit that we can have is a normal hash function. Here is, for example, SHA 256. So in this case, we can send somebody h of r, a result of the hash, and then prove that this is not just a random number. That's a number that has been generated with an R, but without revealing the R. So in this case, we would send h of R, we will send the proof, and then the verifier will be convinced that the prover knows R in order to generate h of R. So let's see a more practical circuit. For example, let's do a simple voting. Okay, this is a very example, a small example, but I think it's very illustrative how it works, zero knowledge. For doing a voting, first we need to know what's the census, who can participate in the voting. So let's imagine that we have 4 persons, each of one has his public-private key, and we have all the public key in a Merkle tree like that. So we hash the public key, and then we create this Merkle tree of all that. So just easy, simple, a normal Merkle tree. So if you want to prove that specific public key exists in the Merkle tree, normally we would do just a normal Merkle proof. We see it was the key that we want to prove that it's in there, and then the siblings of the Merkle tree until we prove that it matches with the root. But what happened when we put this verification inside a zero-knowledge circuit? In this case, the zero knowledge, the program, the statement, this circuit would be a verification circuit. So as an input, we would put all the siblings, the public key, and the output would be the root. In this case, the inputs could be maybe private. So we could prove, for example, that we know a public key that can vote. Of course, this is very useless at this point, but because we said before that the census is public, but we see that we can start having a little bit of anonymity here. Okay? Another zero-knowledge proof that we can do that's also very interesting is, for example, generating a circuit that generates the public key. So the input is your private key, the output is your public key. So mainly what you are proving here is that you know your private key. This is in normal cryptography. This is, I think it's called proof of custody or something like that. But in general, it's done by signing your public key. When you sign your public key with your private key, that means that's a proof that you have your private key. Well, we can do exactly the same with zero knowledge. We can prove that we know our private key. But what happened when we put these two circuits together? In this case, we have a more interesting circuit. Here imagine that as an input, we have our private key, we compute the public key, which is also private, because it's internally in the circuit, okay? And then we have the hash of the siblings of the Merkle tree. So here, this circuit, we are proving not that we know a public key. We are proving that we have a private key that can vote. We have a private key that belongs to the tree, but without revealing who am I, without revealing exactly which private key is, because all this side is private. So here you can see that, well, with this we could start voting. We still have a problem. People could vote twice. But with this, we can vote anonymously, in this case. So how we fix the thing that we cannot vote twice? Well, we do a little bit more of work. And mainly what we do is we compute with our private key and a voting ID. This voting ID is a constant. Let's say it's just the voting for this event, okay? But just a random constant. Everybody knows this constant. So when we hash our private key with the voting key, we generate a nullifier, which is public. So when we are going to vote, we will tell this nullifier, okay? So what will prove this circuit is that, of course, we can vote, and that the nullifier is valid. And as you can see, only one nullifier is valid. And it's impossible to go backwards because we cannot reverse the hash function. So the only thing that needs to do, maybe the smart contract that's collecting the votes, is just having a list of nullifiers, and if somebody tries to vote with the same nullifier, just don't let them. Okay? But as you can see, the nullifier is not related. It's impossible to know which nullifier belongs to which private key. So as you see with this simple example, we can create easily a voting, an anonymous voting system using just zero-knowledge technique. Okay, so I think this is a good example to understand a little bit how zero-knowledge works. So, well, here in Iden3, we have developed some of the tooling for working of zero-knowledge. We are not the only one that they are developing these tools, but we have a set, because we have a set of tools that you can work with. The first is Circom. Circom is a language, it's a programming language, a compiler, where you can generate these circuits. For example, generating all this gray, how you generate that in order that can be used in a zero-knowledge. Well, you need to create this circuit. In the case of Circom, it's a DSL language. It's a circuit that's, mainly you work by small components and joining them to bigger components and bigger components, very much as if you are designing electronic circuits. So you are building more complex components through the smaller components. This is the main, so this is very much how it works. And we have a huge set of libraries that, with hash functions, with, public key, private key generation, with the baby job. Even we have a Merkle tree, a sparse Merkle tree. So you go, for example, to Circom lib. There is a lot of actually code, a library that with many circuits that can be used for doing many of those circuits. Another is a Snark.js. Snark.js is an implementation of the zero-knowledge of the Zika Snark protocol in JavaScript. It's well, it's not. It's like the first. It was like the first iteration, and it was very good to understand the protocol. It's very useful for academic users, but it's quite slow. It's writing JavaScript, and JavaScript, as you can imagine, is not the best language for writing cryptography, but works. It's like writing in Python. Okay? And then once we want to go more production and we want to use this in a real environment, then we start creating Websnarks, which is what we are talking here. Websnarks mainly is implementation done of this protocol in WebAssembly. WebAssembly, as you know, WebAssembly is a virtual machine. So it's a virtual machine that's running in the browser. It has their own opcodes. Okay? In the normal way of writing programs with WebAssembly is using normal high-level languages like C or like Go or like Rust. But the problem of doing this is that it's very slow, especially when you are working with these low-level primitives, now doing multiplications, Montgomery multiplications, modular additions, all these low level with big numbers, it works quite slow. So the strategy here, in order to go fast, is to just try to write by hand the WebAssembly, the opcodes directly, as if we write in assembly. WebAssembly, I tell you beforehand, has some limitations. First of all is that, for example, you can only do multiplications on 32 bits. Of course, you can do it, well, you can do it in 64 bits, but you don't have the high part, the high side, and the low side. You only have the low side. So actually, if you want to do a full multiplication, you can only do it in 32 bits. This gives, just by start, a reduction of 4 times compared with a host. So WebAssembly, the current version of WebAssembly is going to be at least 4 times slower just because of that. This is going to be fixed. There is a new version of 64 bits WebAssembly, and in the new versions will be fixed. The other limitation that we have is that we don't have, in WebAssembly, we don't have multi-thread. Right now, there is a, well, actually, Google has like an extension. So in the Chrome, you can actually run WebAssembly in parallel. But it's disabled for security reasons at this point, and it's not fully standard yet. But it will come in, I hope that in short it will come. Until now, what we are doing is we are using web workers. And the other thing, of course, we don't have any user-specific machinery. For example, Intel's have these parallel multiplications and some specific opcodes that have some specific processors. So we can, of course, we cannot use all these specific parts of the processor. Yeah. So how it works? So more or less, what we have been doing is, I want to show some code here. So what we have been doing here is mainly using JavaScript as a macro language. People that's old maybe remember something that was called a macro assembler. This is quite similar, but it's written in JavaScript. So mainly what we are doing is a JavaScript code that generates a code that generates a WebAssembly. So we are not really writing WebAssembly by hand, but we are using WebAssembly to generate the code. So we can generate a code that's exactly the code that we want. For example, we can generate an addition that's absolutely unrolled. So we have exactly the instructions, the perfect instructions that are the most optimal possible in order to generate this addition, or the multiplication, or a Montgomery multiplication, or any other primitives that we have. So here we have a tool that's called WASM Builder that mainly what it does, it helps to do that. So you can start concatenating codes, and maybe you are putting that in a loop, so the codes are generated you can generate that. And you can do it at runtime, you can generate it before, and then generate the WASM file, and then create in there. So we have all this library and all these machines that, for example, that generates a multiplication. But as a parameter in the compiler, you say, for example, how much big should be the big numbers, maybe 256 bits or 700 bits or whatever, and it generates a code that's optimized for that size, for that bit size. So this is very optimal, and I would say that's, well, maybe it's beatable because compilers in general used to get better, but right now we will see later that we are getting in doubly faster than any other compiler is doing. So let's continue the presentation. Oh no, this is. Okay, so in order to compute a proof, what operations are inside the Snark? So what are the primitives? Actually, what we are doing. Okay, for computing a proof in zero knowledge, mainly there are 2 things. One is what's called multi-exponentiation. Multi-exponentiation is you just have different points, in elliptic curve points, different scalars, the lowercase parts, and then you are doing this operation. It's a scalar times a point, plus a scalar times a point, plus a scalar times a point. And you do that many times. This is what we call as a multi-exponentiation. As you can see, this is a very parallelizable function. You can parallelize that as much as you want. It's very, okay? And the other part that right now with a small circuits is not the bottleneck, but when you go maybe with a bigger circuits, is going to be the bottleneck because the first one is ON. The second part, which is the FFT, is N log N. So this log N at some point will cross the lines and it will be less efficient. So we have mainly these two functions. So if we go to growth, what we are doing is 3 multi-exponentiations in G1, which is a curve, a normal, what you understand as normal curve. 1 multi-exponentiation in G2. G2 is also a curve. It's all the same, but it's an extension field. That means it's like, for example, we are working with a complex number. So the numbers, instead of having just one number, we have the real part and the imaginary part. So, for example, multiplication is not a normal multiplication, but you have to do 2 multiplications plus 1 addition and other. So it's more costly in general. Then we have an FFT, and the result of FFT, we need to do, again, a multi-exponentiation in G2 of FFT. So this is very much, and you can, the number of this is very proportional to the complexity of the circuit. Okay, so this is very much what in growth 16 we need to do for computing that. Okay, and here are some of the results that we got. Of course, this is relative numbers. This isn't a random computer. Thank you, Adria, if it's here for doing all these numbers. Here, the important part, I don't know if this works. Yeah. So here, the important part is you compare the Websnarks number, compare, for example, with the Bellman. So this is a Rust compiler. So this is, you can see here the difference between one another running in one single thread. Here, of course, when you go to 4 cores, then you divide that by 4 very much. If you compare to normal host, you see that more or less is 4 times, it's around 4 times less. This is because the 32 multiplications. But you can see that, for example, for a 50,000 constraints, which with this number, for example, you can create easily a voting system for, for maybe 4 million persons. So a circuit that looks like that would be around this number of constraints. So you can, these are the numbers that we are getting. So 6 seconds, well, waiting a person, for example, for voting or for generating some kind of proof, 6 seconds, this is something that starts being doable. Okay, if you go to 21, 34 seconds, this is much worse. And when you go to mobile phone, you need to more or less multiply that, but at least by 3, depending on the mobile phone. Okay. Another thing I want to mention is that Websnarks is not only for generating the proofs. It also actually can also verify the proofs. Right now we are working with, well, we have it implemented in 2 curves, in BN 128 and MNT 6753. Here are the most used curves in the space for zero knowledge. The first one, BN 128, is the one that works in Ethereum. It's the original that the Zcash protocol used. Right now, it's not considered very secure. It's around, I think it's something like around 100 bits only. So it's not the most advised curve to work with. It's still safe, but it's in that limit. Okay. Actually, Zcash just moved in the sapling version, just moved to the second curve, to BLS 12381. That has it works with fields of 381 bits, and it's more safe. It's considered more safe. Okay. Then we have MNT 6753 and MNT 4753. This is a very, very interesting curve because with this curve you can create recursive snarks. With recursive snarks, you can start, well, you can handle a lot of things, for example, for scalability. You can create a proof that proves another proof. You can create, for example, a tree of proofs for example, and delegate the generation of the proof to many servers. You can create, for example, a chain of proofs, so a kind of blockchain, but with proofs, so a proof that is a proof in a way that, because it's recursively, just verifying the last block means that you verify the full blockchain without, without having to have all the blockchain beforehand. So that's an important one. And cockpits is, well, this is used in Zigze, and this is just a recursive. It's recursive, but just one level. Okay, in some applications with a single level of recursion is enough, and here is where it's using here. Here are, of course, there are more, but these are the most common and the most usual ones. And here you see in the right the times that we are getting in the browser, more or less, in order to verify that. BN 128 is around 30 milliseconds, and the MNT 6753, which works with 700 bits, it's an important curve. The verification time is only 125 milliseconds. That's quite good. Here I want to show a little demo how this would work. It's very difficult to show a demo of that working because it's just here is in the BN the BN 128, so it's due the verification. These are 50,000 proofs, and you can see it that it takes less than 5 seconds. And here is the proof. And actually, we can verify that. So if we verify that, it's, well, it says it's good, but it takes just 22 milliseconds in this case. So this is quite fast. If we go to the MNT 557, here is, well, this is the, I'm going to run this. Let's see, I don't know if it's running. This will take a little while because now here it generates a proof. This is taken from the CODA protocol. They had a standard, reference implementation. It was written in some languages that it's very slow. And here are the timings that we are getting. So the original implementation, it took like 12 seconds to compute, the reference implementation that we had, and this implementation, it takes less than around 100 milliseconds. So if we run here, for example, we can see that we are generating, here are validating the proofs in this MNT, in this recursive snark curve. So this is mainly the demo of what the web library works. I just want to go backwards and show something that I think it's important. That's here. Here is, okay, we have in the example that we had before, we had the circuit. In this case, it would be my circuit, you will use Thircom in order to generate the compiled version of Thircom. The Thircom generates mainly two things. What's the constraint system? It's called mycircom.json, and it generates also a code that computes a witness. Compute a witness means that executes the circuit. So you would put the siblings, in the case of the example, it would put the private key, and it will generate all the intermediary signals and the output, so it actually executes the signal. So with this, we will need this witness.json, we will need it. This is all the values of all the signals that the circuit generates, okay? So once we have the circuit here, we have the setup. This is probably the worst thing of the Zcash technology, that we need this trusted setup. This is, in general, is done with a multi-party computation. This is something that we need to do only once per circuit, but we need to do for every circuit, at least with this technology. There are some papers that they can improve that, and they have universal setups, and it should be possible not to run it in every circuit, but at the current in this version and right now, we have to do this trusted setup. And then this trusted setup generates mainly two keys, the proving key and the verification key. The proving key is what the prover does, that maybe the prover, what it takes this proving key, it takes the witness, so it takes the execution of that circuit, so the circuit that's executed, so this instance of the execution of the circuit, and generates the proof. And the verifier takes the verification key generated from the setup phase, it takes a public key and generates a verification. And well, with this, you can verify and say if this proof is valid or or not. This is an important piece. You see how it works all together. Yeah, and that's my need. I don't know if you have some questions about that. Okay.
Hi. Does Websnark support a multi-party trusted setup at the moment, or
what?
Does the Snark.js library support a distributed trusted setup at the moment?
A distributed trusted setup?
Like a multi-party computation.
Websnark is right now here, and well, it's good because this is when I want to talk in the future. This is very much in that. So the idea is right now it only generates Websnark. It's only the proving and the verification part, but we will implement the setup part. So that's this multi-party computation will be implemented in Websnark. So in this way, we can obsolete Snark.js. We will keep it for academic purposes, because I think it's a good code to learn how Websnarks, how Snark technology works. We'll also, another improvement, but right now the code to generate the witness in Circom, it's a nasty JavaScript. It's a JavaScript that works, but we are going to replace that so it generates WebAssembly. So, and then the other thing that we are going to do is Circom. That's like the first version. We are planning to generate a version 1.0 that's more production ready, that can be audited and that can be, with having a very good specification, taking all the learnings that we had during this year for many people writing codes in Circom, and trying to set up like what would be a 1.0 version of the Circom. That's very much the plannings that we are running, that we want to run in the next month.
Hi. Is the demo available on GitHub?
A demo, yeah. Everything is open source. Everything is in GitHub. You can go to Iden3. You can go to Iden3 repository. You can download there. You can play there. We have also a Telegram group of Iden3. You can, if you are using that, you can connect there. We will answer any questions you have on that. So, but this is a tooling that's absolutely open, and we write that. So we write that because we need it in Iden3, but we write that also because we believe that many other applications in the space will need it. So yeah, absolutely. So it's open source. Free software, so sorry. Any more questions? Oh, but that's it. Thank you very much.